Hello, everyone, and welcome to the UC San Diego CSE database seminar. Today we have Professor Frank Wuerthwein. I hope I'm pronouncing his name right, surname right. Frank, you should let me know. It's exciting to have him. He's a professor in physics and the Halle-Jolo Data Science Institute, and he's also been working with the San Diego Supercomputer Center. He's been working on a lot of data infrastructure and data management issues in high energy physics, specifically related to the Large Hadron Collider. And that's what he's going to be talking to us today. So I think this is the first time we are seeing the title have the word exabyte in it. So really have you here, Frank. Go for it.
Okay. There we go. As you'll see in a moment, I have to always start talks like this with a disclaimer. Any opinions expressed here should not be misinterpreted as the official opinions of the CMS collaboration. And the reasoning for such silly disclaimers is that I'm working in a socio-political science endeavor in an environment with 4,000 people, 200 plus institutions across 40 countries. And if I waited for a CMS to sign off on this talk, there would be no talk because it's just too complicated to get everybody around and agree on something. And given what I'm talking about is effectively R&D ideas, those are by no means accepted as the right ideas or even the right direction necessarily uniformly across the LHC. So take it as my take on what the LHC needs. And I want to start the first 10 minutes with an introduction of the science that we do for computer scientists. So I have to always show you the collider because this is an aerial view. The yellow line is where the actual collider is underground. You see the airport of Geneva here, and you see the Mont Blanc in the background and the Lake of Geneva. So this is a big science project. This is the detector that we operate. It's about 5 stories high. The by numbers, the experiment by numbers, it's 80 million electronic channels. We digitize into 4 bytes. We digitize at 40 megahertz. So if you multiply these numbers, you get about 10 petabytes per second of information. We then do about a 1 in 1,000 zero suppression, and then we filter collisions. Well, I'll explain what a collision is in a second, by in 1 over 100,000 roughly. So today, so far, we are taking roughly, when the collider runs, 1,000 megabytes per second of raw data to tape. We don't run the entire year, so we get to about 10 petabytes of raw data per year. And what you'll see in on this slide here is this is today the first row. The second row is by 2028. We are envisioning an upgrade program that gets us from about 20 petabytes per year to about 600 petabytes per year. And that's where the exabyte reference comes from. And so what's happening? The beams get brighter by about a factor 6. The dating rating date goes up by about a factor 6, and simulations go up by about a factor 3. Now, what do we do? Let me make sure, okay. What do we do? We collide in this Large Hadron Collider. We collide protons against protons. You should imagine that there is a spindle hair thin and about 5 centimeters long that whiz around the 27 kilometers of beam, and every 25 nanoseconds, 2 of these spindles go frontally through each other and lead to today about 30 collisions of proton on proton. And when the brightness of the beams increases, to about 200 collisions proton on proton. And the science in a nutshell, we measure, this is the ultimate counting experiment in some funny ways. We measure corrected yield. In other words, we measure collisions, number of collisions of a certain type. And a corrected yield you get by you observe beam crossings that pass some selection. And then you divide by the selection efficiency. And in order to determine the selection efficiency, you need simulations. And in order to develop the selection, you also need simulations. So the entire enterprise is very oversimplified, encapsulated into a single equation. You measure something, you want to extract something that is actually fundamental science, and you have the brightness of the beams that is measured separately. And so you divide the counts that you have by the luminosity, and voila, you get the cross section, which is the thing that you actually are after as a physics science measurement. Now, what's actually happening and how do you do science with this? I call it the Big Bang in the laboratory. We gain insight by colliding protons at the highest possible energies and highest beam brightnesses that humanity has managed to achieve. Then we measure what gets produced and how much, meaning how often, the rates. We measure the masses and lifetimes of the objects that get produced. We measure their partial decay rates into all the different things that they decay into. And from these kinds of measurement, we derive the spectroscopy as well as the dynamics of elementary particles. And progress is made by going to higher energies because you can produce things, the things that you can produce have larger masses, and then by more proton-proton collisions, because the brighter the beams, the more rare phenomena you can study. And for non-physicists, spectroscopy means what are the particles that exist and what are their properties. And dynamics means what are the forces, how do the particles couple to the forces, how do these depend on energy, angular momentum, phase of the moon, whatever. So this is sort of the physics program, and that's all I'm going to say about the physics. The reason why I front-loaded this is I want you to understand, because in my mind, the physics itself, the fundamental science we do, derives everything else. It derives the data formats, it derives the challenges we have, it derives all of the technical solutions between the physics we try to accomplish and the sociology that we live in. That are the constraints that ultimately determine the systems we build and the infrastructure we run. And so to give you a sense of the basic data flow today, there's the 10 petabyte per second of raw information, trigger and zero suppression, I talked about this, gigabyte per second goes to tape and goes to a prompt reconstruction. And the tape itself, there are two tape archives. There is one backup at CERN itself, meaning at the site of the experiment. And then there's a second that is distributed across 7 locations, 7 national labs worldwide, the US providing 40% of the tape capacity. And then in addition, we do simulations, and they also go to tape. What can actually be analyzed is determined what you then recall from tape to disk. So all subsequent processing and analysis starts with a decision of what data stays on disk and for how long. And we run today a 150 petabyte global disk-based data federation, meaning you can go to your Starbucks in San Diego and access any byte anywhere on disk, anywhere in the world, as long as you are have the right authentication. And the authentication is presently X59 based on your person. So in addition, there is a 200,000 core processing capacity across 50 to 100 clusters. That sort of sets you the scale of what we do today. And I'll talk about first the nature of the data and then where we go in the future. The nature of the data is fundamentally, you should think of as a 2-dimensional problems. One axis is events. Events just means the collisions. Given that this is a fundamentally stochastic process, meaning whatever happens in a collision is a random choice by quantum mechanics or nature or whatever you want to call it. And so it's not predictable. It has to be found out. So the events we have is the information we have on one axis. And then the other axis is all the objects that characterize an event. And depending on what level of processing, you have different objects and different data formats in your y-axis, whereas the x-axis is basically the same for all data we have. And so what I want to start with is I contrast the processing use cases in this context, in the context of this being a 2-dimensional event format. And I'm doing this in order to convince you that we actually have 2 problems rather than 1. And so this fundamental 2D space can either be via the primary processing. In the primary processing, every object is touched in an event, and every event is touched. Because the primary processing you should think of as the raw data gets processed into something that is usable for analysis. And we, as I will show you later, we have a sequence of formats of differing complexity or utility. And I'll explain what I mean by that more in a second. So in the primary processing, you take about 20 seconds on a recent physical core per event, and we're slowing down by a factor 24 because the occupancy of the detector goes up, therefore pattern recognition becomes much harder. And the science analysis, on the other hand, touch very sparsely. They typically take only 10% or less of the data per event, and they operate today at 10 hertz on the official data per core. And typically, people like myself make themselves private data samples, because on those private data samples, we then typically run on 10 kilohertz. In other words, we make private data samples for two reasons. Three reasons. One, to filter events. One, to throw off stuff that we don't need out of the objects. And one, because our private, the speed with which our private data can be searched through is 3 orders of magnitude larger than the speed with which the official data can be searched through. And that I won't go into why it's complicated. In one of the objectives of the Hadron LHC is to achieve on official data what we currently achieve on private data. Now, if you digest the previous page, it becomes obvious that we have two problems. We have a primary process problem of order 1 exabytes, the 600 gigabyte I mentioned earlier, per year, and it takes order 100 seconds per event per core. All data in the event is accessed. And then we have science analysis of somewhere between terabyte to petabyte, depending on analysis, where you're accessing order 10 kilohertz event rate per core, and you're only accessing a small fraction of the content of the objects per event. And so these two access patterns differ so dramatically by so many orders of magnitude that I personally think of them as completely independent problems. And my thinking is that we should solve those two independently. So I will walk you through the kind of challenges for each of them separately. So the primary processing problem we'll start with. Each of Atlas and CMS wants to do their annual processing campaign of the previous year's data and simulations during the first 100 days of the new year. This is just the way that we operate. Basically, we run in the year. The accelerator runs from about roughly February or so, sometimes March, until about November or sometimes December. And during winter, the accelerator doesn't run because the electricity cost is too high. And Geneva needs electricity to heat houses, basically. And so the accelerator is shut down. And so that gives us a natural cadence and therefore a natural way to do the processing. Roughly 40% of this is done in the US at 2 DOE national labs. For my experiments, everything is done at Fermilab. The use as portion of processing is about 400 gigabit per second for 100 days, if you go through the numbers. And even if you were only looking at CMS and only looking at raw, you're actually still at about 100 gigabit per second nonstop for 100 days in the US alone. So these are very large processing challenges. The technical things, in some sense, they are pedestrian, but they're just massive and therefore non-trivial. They cost a lot of money. So there's tape recall. We estimate that tape is about a factor 3 to 5 cheaper than disk at the exabyte scale. And therefore, we try to use as little disk as possible. And therefore, we have a tape recall problem and need to procure enough tape bandwidth and be able to do that reasonably and predictably. Then we have a limited disk buffer at the archival tier 1 to prepare data for transfer across the wide area network. We then have to manage a terabit per second network. And these are all numbers for 2028, basically, because this is where we're heading. So imagine that the DOE gives us an exascale computer to do this with. Then we'd want to send data over in a terabit per second. There are bursts, network transfer has to be managed, etc. the disk buffer at the far end has to be managed. The computing has to be scheduled with the processing, and the processing has to be co-scheduled with all of this. And all of this has to be done in an agile enough way, such as to minimize all the buffers to conserve money. And so if you want to look at it as a picture, while we're doing all of the buffering and bringing off from tape in order to feed something like NERSC, at the same time, raw data, new raw data that's being taken with the detector overlaps partially with that 100-day processing. And so you're going to ingest 300 gigabits at 50% duty cycle while you're putting to tape 2 times 2, 200 to tape and 200 from tape at about 100% duty cycles, while you're sending at about a terabit to processing centers with the 20% duty cycles. Those are sort of the rough numbers that we're throwing around right now as design numbers for a system that we're building. And current estimates of CPU time required or processing time required would keep 55,000 nodes of an exascale system 40% utilized for 100 days. It is highly unlikely that we will get 40% of a DOSE exascale system for 100 days. Much more likely is that we will have order 10 processing centers, some from the NSF, some from the DAE, some from universities. And so you're going to have a distribution to about from 1 to 10 in the US, give or take, which is going to be interesting and makes this a little bit more complicated. I'm now going to switch gears to what probably is the more interesting challenge to people like you guys, because it's much more involved in terms of access patterns. And so I'd be happy to accept that if somebody in the audience tells me this is just brute force and there's nothing interesting here. And so I accept that. I think I'm hoping to convince you that in the analysis challenge, there's a lot more interesting things to think about. So the basic sociology is that there's 1,000 scientists out of 50 countries who want to have access to all of this data in order to compete with each other. So the basics, my basic picture is that we collectively produce the primary data sets because we collectively operate the detector, operate the simulations, build the software, et cetera, et cetera, et cetera. Once we have primary data sets, all hell breaks loose and we compete with each other tooth and nail for the best ideas, the best innovation in science. All of this happens on a fixed infrastructure, more or less, that is provided to us by the experiment as a whole. And then we again converge on the publishable results that they all can agree with, where reproducibility comes in, et cetera, et cetera, et cetera. And so, and this enabling competition is really the driving factor, because enabling competition enables innovation. And that drives us towards a pyramid of sorts of data formats where the raw, the AOD is derived from the raw, the mini is derived from the AOD, and the nano is derived from the mini. And we need to go back every now and then, and I will describe to you what I see as the access patterns in analysis and the kinds of system ideas that we're throwing around right now that I hope is sufficiently interesting to warrant me giving this talk at your seminar. And so the way to think about this is that you start with the raw, which is the most flexible, but also the slowest, where you have 500 seconds per event per core in order to make this first step from raw to AOD. Whereas in the opposite direction, on the nano, it's the easiest to use for a researcher. It requires the least amount of expertise. It is the fastest and runs at about 10 kilohertz per events per core, of events per core. And it is really these last two data sets that I hope and expect and what we're designing for as being the primary data sets that people will use, that 1,000 people will get at, because we can't afford, this data set is too big and too cumbersome. If we have to analyze, go back there, our analyses will be not very agile. In addition to this, I have to do an aside on simulations, because the simulations in itself bring their own kinds of challenges to the overall system. And it's not the producing of the simulations, but it's the analyzing of the simulations. And for that, you again have to understand a little bit of our science. The science program is exceedingly diverse. My experiments has by now published 1,000 papers in peer-reviewed journals in the last 10 years. There's about 100 papers per year, give or take. So in order to produce one paper, there are in order to do the entire program with thousands of small samples of limited physics interest, plus tens to maybe not even 100 samples of very broad physics interest. And I'll explain this in a second. And then each analysis needs some of the big ones and lots of the small ones in order to do this. And so the dynamic range of what people access is very, very large. And I'll show you this in a slide in a moment. So you have an enormous diversity of access rates and interest in these different things. And fundamentally, I believe it's predictable, even though today we don't predict it. And I'll talk about that in a moment too. Here is the next two slides give you a sense of the scale of the diversity. This here is the sample size and number of events versus the fraction of the total sample count. What you see in this plot is that 70% of samples are of a size of less than 100,000 events. So 70% of the samples is what I would call small. The total campaign has 12 billion events, and there's 14,000 samples in total, just for one campaign of 1 year. This is 2016. Then you can look at this inversely and ask yourself, how many samples make up the total data in terms of event count? 80% of the total number of events are in samples greater than 10 million event samples. So basically 80% of the total data volume, because events have roughly the same size, is in very large samples. At the same time, 70% of the samples is in very small samples. So there's an enormous diversity, an enormous dynamic range. And what you should conclude from this is that most individual samples are very rare, meaning they're rarely accessed, they have little interest, and then there is a few whoppers that everybody wants. And so what you end up having, therefore, if you measure file reuse as a measure as to indicate where caching strategies come in and so forth, you will find that it's a hyper-exponential. So this here is the number of files that have been accessed this number of times during a month last year. Basically, July 15th to August 15th at the Tier 2 center. This is the Tier 2 center across Mayer Hall and SDSC is about a 10,000 core, 5 petabyte disk space kind of infrastructure. And this is the kind of use that we have seen on there. So you see that there is a few samples that are very popular, and then lots and lots of samples that are not very popular.
Frank,
yep.
Frank, sorry to interrupt. I have a quick question over here. These this widely different access frequencies, are they predictable? Do we know which files are going to be the most popular and most accessible or most accessed? Or
I believe that they're predictable, and let me explain to you why I believe that. Because I predicted it in the early years.
Okay.
Meaning, in the early years, I was in charge of the global distribution for all the data of CMS. And so I basically decided how many replicas should there be of any given data set and where should they go.
I see.
And what did I use? I used my domain sign knowledge, and I used my being clued in on where we're at in terms of transitioning from one version of the data to the next version, basically between releases. I knew exactly what my group and most other people used as release to access the data. I knew what was coming out, where was the current development path, at what time roughly will we be changing, and when those new things arrived, I knew that people will switch, and therefore I could predict as new data sets come out based on the content of the data and based on the release version that this will see a lot of use within the next weeks or months.
Got it.
Does that explain?
Yep, that makes a lot of sense. Another question was, do these research groups that get these data for their publications and research, do they access different kinds of files, or do some groups primarily focus on certain kinds of events? Just curious.
So that's a good question. In fact, the diversity here expressed is in part because every imaginable piece of physics that anybody could possibly want to do needs to be simulated.
Mm-hmm.
And therefore, most of these small samples are individual requests by a single PI or a group of PIs or a group of students who wanted to do something new and different.
Got it. Okay.
And so the diversity comes directly out of the diversity of the science program. And so in a nutshell, the large background samples that everybody uses are popular and big. The small individual esoteric science projects that only a few people do, they are small and only accessed in certain places where certain people do their work. Does that make sense?
Got it. Okay, thank you. And just, I think I forgot to mention this at the beginning. Audience, if you have quick clarification questions, please raise your hand and I will pause and I will ask Frank, or you can unmute and ask, but please raise your hand first. Longer questions, we can keep till the end for a longer discussion. Thank you.
Yeah, I love being interrupted. So
okay.
If you want to interrupt, go for it. Now I want to, in order to deal with this, we've come up with something that we call data lakes model. And I want to explain this and want to I'm going to walk you through more esoteric systems that we're thinking about building. And I want to acknowledge up front that the most esoteric at the end of the talk are the least thought through and the hardest to build, and where we have the least understanding of how one would build those. And so the simple one is we start out with a data lakes model, where the notion is we want to try to have some sort of regional encapsulation, if you wish. And we call those data lakes. The notion here is that there is a global federation of lakes that you explicitly top-down place between lakes. Therefore, we have a top-down data management policy engine, meaning we have a catalog that specifies what files are in what data sets, what exists, policies, this has to be here and here and here, and this is supposed to be only here, that sort of thing. And then replication happens and establishes the policy, turns the policy into reality. And that sort of thing is the transfer between lakes. Within a lake, we can then imagine top-down placement as part of workflows. And I think of this as buffering more, like I said in the first part of my talk. Then there's bottoms-up placement for cache misses. And I think of that should really be the driver for the analysis, because it automatically regulates people who walk with their feet, vote with their feet, choose what they want, and it gets brought to them automatically. And then there is the option to streaming for remote file open. We do this today in order to satisfy edge cases. That's why we built this as a federated data infrastructure that you can literally access any byte that is anywhere in the world on disk. But of course, you couldn't access terabytes from your laptop at Starbucks. They'd throw you out of the door if you tried, and you probably wouldn't fail anyway. And so there is sort of a notion of streaming for remote file open in order to visualize when something fails or whatever for various cases. And we're starting to explore by a mix of R&D pilots and production pilots the features of this model. So let me describe one such pilot. And one such pilot is a production scale caching pilot that is primarily distributed between San Diego and Caltech. We literally have disk servers in both places, and we have clusters, compute clusters in both places. And the compute clusters in both places treat the servers in both places as if it was one storage system. And the one storage system then brings in cache misses from the global data federation as necessary. And having this production prototype is useful for us because we can then measure in in reality of what our current use patterns are. And that's what we have actually done. I'll show you plots. Now, we define a working set as the sum of sizes of all files accessed in a time period. It's a operational definition which is relevant for our caching infrastructure work. A working set is effectively what you'd need in order to be able to maintain appropriate disk space to not have thrashing beyond some kind of time scale. And what I show here is distributions of working set sizes for simulation and data for different kinds of time periods. If I take a weekly, then I get that kind of distribution. If I take a daily, I get this kind of distribution. A weekly, I get this kind of numbers. And for the monthly, I get this kinds of numbers. And to summarize, you find the obvious. For the daily to the monthly, you go from a few tens of terabytes is the working set per day to a few hundred terabytes per month. So right there, from a daily to a monthly, you're going by an order of magnitude roughly in terms of trade-off between disk space and network use. So if we're willing to use the network to support the dailies rather than the monthlies, then we can save as a factor of 10 in disk space. The obvious, right? So none of this should be rocket science because it's obvious. And then if you take a monthly, you're looking at something like 451 terabytes for the month of October, for example, in 2019, just to sort of give you a sense. Now, if you then actually look more fine structure and plot this as a function of day, the daily reuse is sort of roughly sits somewhere between 1.5 and 2 over the entire period of time of the previous size. And the identification here is if all files are accessed, if all files that are accessed only once, then this reuse would be 1. If each file in a working set is accessed 2 times, then the reuse would put 2. And you, of course, have an average defined because some files get accessed more often than other files. And so that's sort of, I put these numbers in so they give you a sense of scale. In addition, we also observe partial file reads. Our applications open to the file and then sort of we have an access as a format that is basically built around vectors of byte reads. So, vectors of byte ranges. So the application calculates a vector of byte ranges that it will access, then it hands that vector of byte ranges to the server, and the server prepares that vector of byte ranges and gives it in one fell swoop back to the application. And so there is, in a sense, a transfer, a data access format, a file access format a file access protocol, sorry, that supports the fundamental science that we do by supporting partial file reads. And we do this via the wide area network as well as locally. And this is sort of what you see locally for analysis at UCSD during this time frame. And now let me make contact again to what I said at the very beginning. I told you that we have a 2-dimensional structure of our data. What you've just seen is effectively that an analysis typically loops over the event dimension, accessing some objects, few of them, and then when it finds something of interest, then it accesses additional objects. And this is the fundamental science-driven access pattern, because all we do is we select events, and once we found something that's interesting, we then go to town and say, okay, for this event, I also want to know X, Y, and Z else. And so that is the natural pattern for the science that we do. Now, we have developed a data format in order to support that, in which I've sort of tried to describe here, which also provides us data integrity. We put objects in the Y dimension. We have all the objects. We put them in different colored baskets according to the object type. And then we form a basket out of many events. And then we zip this basket via some kind of zipping algorithm, meaning compression algorithm. I don't want to go into details what we use. It's to optimize, to minimize space at present. And so this is sort of the data layout that you actually have on disk. So when the application says, I want the byte range from here to here, then we have to unpack 2 baskets, send it to the application, and the application actually does the decompression today. And therefore, if you have a bit flip anywhere in the file, the application would barf because it will be unable to read the data, and it will basically crash or exit with an error. I wanted to, now that I've explained to you pretty much all there is to know about how we do the science and how the data format works and what kind of typical access pattern there are, I now want to go into 3 R&D topics that I consider near term, and then I'm going to tell you the more esoteric stuff that is longer term. Near term is the first thing that Arun already asked about. Can we build better cache miss algorithms than least recent than an LRU? And I am firmly believing that we can do better than LRU, simply because I was the caching algorithm. My brain was the caching algorithm when we started this, before we started LRU. And so I know that I didn't do badly. I know that LRU currently does better, but a perfect algorithm would combine my brain, my knowledge as a domain scientist with an LRU. And I think that's a research topic in its own right. And I think this is described here. And it is already what I told Arun earlier when he asked the question. We could detect when new campaigns become more popular in real time, and then therefore switch to predictive and cache things and no longer cache things, pick deletions accordingly. In other words, via AI, via machine learning, learn iteratively as a function of time what is the right things to stay in cache and what should be deleted in order to minimize cache misses in the end, or minimize data transfer across the wider network. And we can argue on what exactly should be minimized about here. So this is an obvious place where a new group could have an impact in. Moreover, we built our caching infrastructure software such that we actually have a plugin place where we can replace LRU with any algorithm you want. So we built the infrastructure software such that we could have a group develop a new algorithm that takes different additional information into account, and then exercise that new algorithm on the production testbed and prove that the new algorithm is better, whatever better means, than the old algorithm. So this is actually something that we could really turn into a project and execute. Next thing is, there is a fundamental sociology in geography. We have a lot of the people who have money. Basically, if you look at the world, the people who have money live either in Europe or the US to first order. And then you have some people who have money in Asia. So we have, therefore, a fair amount of European hardware infrastructure, a fair amount of US hardware infrastructure, and a fair amount of Asian hardware infrastructure, and then very little in between. There's a little bit in Russia, but the big economies have the big money, therefore that's where the infrastructure sits. And so, therefore, if you then look at the world, given the bifurcation of Europe, a perfectly obvious design criteria for the IO stack is to be sufficiently latency tolerant to lose less than, say, I made it up, 10% CPU time for access distances of 500 to 1,000 miles. And so in order to support regional caches that span European countries. And that sort of is actually something that is literally pursued, especially strongly by the Italians for the obvious reasons of geography, right? Acknowledging this, we added an additional cache to our Southern California cache, which sits in the POP of ESNet in Sunnyvale. It's about, I want to say it's about 5% or so of the total disk space. I don't remember the exact numbers, but it's in that neighborhood. And we record separately accesses to Sunnyvale versus accesses to San Diego and accesses to Caltech, so that we then can ultimately exploit the data analytics that we take to just see what's happening out there in the wild. We've so far mostly taken the data and haven't done the analytics, so I'm showing you only a few GWiz plots. This is the accesses per day, the amount of data read per day. So what I would like to see is detailed analysis on impact of latency on CPU time. And I don't want to go into too much details because it's more complicated, but because you have to account for users, account for different kinds of jobs, account for a bunch of effects that would bias you. But in principle, we have all the information to do this. We just haven't done it. Then the partial file reads, in principle, the way things work is that a user has an application that is theirs, and they will then have a collection of a couple dozen data sets that they need to analyze for their analysis, which is encoded in their application. Now, in principle, we can predict access patterns and exploit them for partial file caching because we know the executable, we know the data set, and we know the files in the data set. We therefore could, in principle, measure the first n accesses to the first file or files. We could even verify that this is actually stable, and then predict future access patterns and prepare the infrastructure for those future access patterns. So fundamentally, all of this is in principle possible. And it's just never been done before. I tried with Carlos Malzahn from Santa Cruz and one of his grad students in computer science to pull this off to show a proof of principle. And it's hard, it's a pain in the neck, but this is doable. We've shown that it is a priori doable. And it would actually be an interesting R&D project to show that what you gain from it. Now I want to switch. Now we're starting. This one was the last of the things that I actually know how to do. Now we're starting to get to things that I actually don't really know how to do. This is ideas only, much more esoteric, much more adventurous in a way. And the first one is that the LHC community as a whole is considering a fundamental paradigm shift from analyzing its data sequentially, meaning every user loops over events, to declarative programming. Because as I tried to convince you earlier, the fact that we loop over events is really not what we do. Because in the end, we define a selection and we define objects we want to have as output. And then in principle, we could declaratively provide that information to some compiler, very loosely define what that means. And then between the compiler and the infrastructure, it could optimize the entire preparation of the data for access by the application. And voila, the end user sees the histograms or data structures that they wanted to see only for the things that they cared about. So that would, if we were capable of building such a system, then the back-end infrastructure would be arbitrarily optimizable. And the rub here is in what you mean by compiler. And there is some work in the community to try to understand whether this is possible. And I am not involved in any shape or form, so I don't really know anything about it. But in principle, this allows much more speculative analytics in the 2D plane of objects versus events. And a way that I can think of about this and actually see my way walking towards it is what I'm going to describe last. And that's sort of the last thing I'm going to talk about. And I'm going to define a number of concepts and then combine them all and give you a killer app that I would love to have as a domain scientist, because that would just make my life doing analysis infinitely easier. The first step to this is to have an ingestion mechanism to an analysis facility that can, where I could tell to this service, I want to filter on events using this code as a filter. And I want you, while you're at it, transform everything into columnar data format so that afterwards I am much faster in reading the data that I have subselected out of this. And I want this to be done for me by some service that fills my facility on which I then work afterwards. So that's step one. You can then put, instead of putting this whatever you call it, this red thing in here, you can put it underneath, in other words, into the file system itself. People in, I'm told that people in the CS community talk about this under, or in industry even, under two buzzwords, either computational SSD or programmable file systems. And as best as I can tell, these two are fundamentally synonyms, give or take. And so how would that work? We could push this down into the file system or into the CSSD as hardware, depending on how you want to swing it. And it would do the same thing as the Service X. It would, in addition, uncompress bucket structure potentially, and so could serve at the lower level rather than at the higher level. And where exactly you do this is actually not so obvious in my mind. Finally, you could combine all of this, and then it becomes actually clear to me, at least, where I would draw the line. And this one slide, in a physicist's way, describes a system architecture that I would love to have as a system, because it would give me everything I'd want to be able to operate much more seamlessly, much more effective in doing my science at the high level of CSE. That's why I call that the killer app. Assume researcher starts with what I told you that is called the nano ID. That's 2 kilobytes per event. I make a loose selection to find interesting events. That gives me a collection, call it election pointers, call it what you want. A collection of events of interest, derived from a format that is actually lightning fast. I can analyze at 10 kilohertz. In fact, I can today do so. It's actually possible. I could even do iterative refinements, because I will fundamentally have to justify my selection by determining the efficiency. So there's actual science that gets done here, understanding efficiencies, understanding purity, that sort of thing. So at this level, science gets done until I realize, okay, this is how far I can drive this. Now I need 1 float or 10 floats or something that does not exist in the nano, or that is broken in the current version of the nano, and the new nano hasn't come out yet. What do? I go 1 data format back up. Now I have to deal with 250 kilobyte of events in the mini. And now I want a Service X to be launched over lunch, night, weekend, whatever is the appropriate scale, and produce for me the nano edition for my format in my analysis facility, such that when I come back from lunch, night, or weekend, I can now again do the new stuff, including all of this extra information that I didn't have initially, and refine my analysis and continue and drive it towards a publication. And access to the custom nano could be via CSSD, because the custom nano does not exist anywhere other than in my analysis facilities, because whereas all public data is stored on tape, if I lose a single byte out of my nano, I'm screwed. I have to start over, because I don't even know. Basically, corruption is my enemy here. Data loss is my enemy. So I would want to probably keep my custom nano of some kind of erasure encoded triple, quadruple, 5-way data loss secured hard drives, because that's cheap. Whereas in order to maximize my access speed, I would want fast random access via automated loading into NVMEs to what I actually do and can do then interactively, so that I can run not at kilohertz. Why stop at kilohertz? 100 kilohertz, terahertz of event rates, because now it's literally is much more akin to a database select, because all of the heavy lifting was done already. And now let me contrast to this so that you understand why I'm so excited about this idea. Is what my group does today. We work on the mini. We have worked on the mini in the past. We're just switching from nano, and it takes us about a month, literally, to take the mini and turn it into a format that we can then use to do science with. There is a month of a student, and it's not just a month of time just processing crap, bit moving and flopping around, that is of no value to the science, other than creating a custom data format that I can then use and be fast with. And it is also that my students, postdocs and grad students, have the erroneous assumption that they've actually provided me value by creating data formats and by creating platforms and analysis as formats in C++, that all they do is produce a data format that I can then do science with. It's a giant waste of human effort, in student and postdoc effort, in order to maintain all of the crap that we need to do in order to go from the format that we have to a format that we can use. If instead, given that I have an explosion of data coming against me, I could get to a system that does this for me in roughly this kind of structure, I could envision being back to physicists doing physics rather than infrastructure. And that sort of is where I would love to see us heading. And in my mind, this is something that I can't pull off with the likes of people in my physics environment. I need people like, and the two people that we've recruited so far is Carlos Maltzan from Santa Cruz, who is of Ceph fame. And then one of the people who is actually involved in this now is Andrew Chien, who you guys apparently know because he used to be at UCSD, the computer science faculty. He's now in Chicago, and he's interested in some of the acceleration aspects of this, of Service X via GPUs and FPGAs. But in my mind, there's an enormous amount of stuff that we don't know how to do yet and could build on things like Skyhook from Maltzan, which is a Ceph plugin to support arrow type data sets and basically a columnar data. And mind you, half of these words that I've just used, I have no idea what they actually mean because I'm a physicist. I got into this business by sort of mistake, and now I'm stuck with it because I've done it for a while. And fundamentally, if somebody provided me something that actually worked in this, that does this, I'd be much happier and doing physics again. And I'd worry about the big wide area network problems rather than these sort of things, which I consider much more complicated. I think that's it. HLHC expects exabyte per year data by 2028. It's a times 30 increase over today. This has led over the last couple of years to a careful re-examination of what we do with our data and why. A lot of what you've seen here, if you had asked me 2 years ago, I would have not been able to tell you because I hadn't understood what we actually do. I had never asked myself that question. And so there was a soul searching of understanding what we do in order to be able to present it in the way that I presented today, because it wasn't obvious. I hope that I've identified promising R&D to save disk space and needs via a mix of network caching, tape archiving, analysis facilities, mix of top-down, bottoms-up, and direct access to data. And maybe I've even stimulated somebody to join as a collaborator. And this is all I had. Thank you very much.
Okay, great. Thank you, Frank. That was a lot of information, very exciting stuff happening at the LHC. We can take questions from the audience now. Anyone has any questions, feel free to raise your hand or unmute yourself and ask.
Hi, Frank. Thank you. This is Aline. I saw a lot of slides that were mentioning variety of data, of sample sizes, of requirements on them, but I'm wondering whether there is also variety in the data models that you manipulate there. Are we always thinking about this tabular? Conceptually, there is a tabular representation when you show that x-axis are the events and then the objects, the y-axis. That looks very much like a table. Do you ever manipulate other kinds of data?
So I'm being very simplistic here. What's actually what is actually one of these boxes, the only simple part of one of these boxes is on the x-axis. The y-axis, you should think of these data as sometimes it's C++ objects, sometimes it's lists, sometimes it's arrays. There's all kinds of structure that a box signifies.
Mm-hmm.
Am I answering in your question?
Yeah.
So it's not so, I've simplified this massively. And one of the things that we are, struggling with in my field, and I have to admit that I am struggling with it myself, and I have not quite completely understood. There are experts in my field that have explained it to me, and I still don't understand. And that is, how do you map the kinds of what I call here an object onto then a serializable data structure in Python, for example? And there is buzzwords like jagged arrays, and there is there's a guy in my field that came up with something called an awkward array in order to map our way of thinking about the y-axis onto something that then fits into, and I'm again using a buzzword that I have no idea what it actually is because I haven't done my homework, into pandas data structures. So I'm much more at home when it comes to cyber infrastructure of the big things. When it comes to the details of the format, the details of one of these squares actually means, I have to admit that I would have to send you to somebody else to talk to. Am I making sense?
Yes, of course. The reason I was asking is there are many, but one of them is connected to one of the more ambitious goals we were mentioning here, namely coming up with declarative specifications of what data you're looking for. And that would go hand in hand with some higher level abstract way of thinking about the structure of the data, so that then you can write pattern style query languages over such data.
Yeah, and there is a project, NSF funded, called IRIS-HEP. It's in a software institute, and within the software institute, that is one of the things that they're trying to work on. And I've not paid enough attention. This is the people that I would send you to, because there is, and I just had, it's not in my wheelhouse in essence. And so and they're thinking about this along those lines, and I am just the wrong person to explain where they're at because I don't understand it myself.
Yeah, I would find that fascinating, and particularly
I can try to get you or somebody, and we can iterate with Arun and you on, why don't I find out, I sort of know who the right people are, and what I would suggest is that I figure out what would be a talk or publication that may have information like this, so that it gives you a sense of whether it is worthwhile inviting that person to this seminar series. And then you guys can take it from there. Because I wouldn't even be able to tell you I couldn't even tell you the right name necessarily, and whether this would be interesting at the level where you would want to see it, because I don't understand it myself well enough. Am I making sense?
Yes, and this is a great proposal. We thank you for the offer.
Great. That would be very interesting. Following up on Alan's question, Frank, are these formats and the types of events and stuff, do they keep evolving, if I understand right? So is that one of the reasons why people still write file format and parsing software from scratch over and over? Or is there some standardization for how you're going to capture the data? And so now you can start commodifying the software stack.
In a way, it is commodified on some level. There are two parts to this. We have a standard software library, a set of libraries, where that allows us to do, now I have to find where that was, to do this here,
I see.
and do this in an arbitrarily configurable way, such that any one of the squares can be anything from a list of well-defined objects, meaning where I mean list as in English, not in list as in computer science, meaning there is a standardized set of class. There's a class library.
Got it.
There's a class library that allows you to pick from what you use to express, and then there is a way to turn multiple of these objects into a basket and configure this when the file is written. And what we have changed and what we do continue to change is not the class library, not the fundamentals. What we continue changing is the physics content of what the things mean that we put into these baskets.
Got it. So the interpretation of the data structures changes, but the data structures themselves are roughly.
Yeah. So from a computer science perspective, the data structure is not changing, because it's at an abstract level, it's cast in stone. There's class libraries. There's all this kind of stuff. That changes very, very little.
Got it.
What does change is how we encode science into these, how we use it. Does it make sense?
Yep, makes sense.
The one place where this is not true is the one place that Aline asked me about, and that is, where was I again? Here. Here, everything changes, because we're not committed to using the things that we've used in the past. So here, in some ways, everything's wide open, because it's not even obvious that, so we're sort of the software package that everybody in the community knows how to use, that encodes our means to write data formats. Giving up on something like this that is well established is hard, right? Obviously.
Yep.
And so the community is not willing to do this easily. And so there is an enormous amount of strife of sorts, and it both willingness to move on and willingness to fundamentally change in order to achieve this kind of a holy grail of sorts. Am I making sense?
Yep, makes sense. The next question I have related to that is, when they start going down to the smaller scales of data across the hierarchy, is that sub-selection only, or do you have aggregation too across the?
You actually, that sort of, how do I do this best? Let me go to, in essence, imagine a physical object like an electron, meaning it actually, and then it goes through your detector and hits all kinds of causes all kinds of deposits of energy and whatnot, and that then becomes digital, encoded into bytes of various counters, right? Or channels, electronic channels. let's start from there. How you determine what is an appropriate object to make out of the fundamentals, which are a 4-byte for a channel over threshold, is different in the different formats. When you look at raw format, you're trying to preserve the full complexity of what the detector saw.
I see.
And then as you go to higher level formats, as you go from the 6.5 megabytes of raw to the 2 kilobytes of nano, you've literally thrown away everything except for the fundamental physics objects, which is then 4 vectors. It's literally 4-vector math that we do in the end. And so there is left of an electron is a few characteristics to allow you to select purity of the electron and efficiency for different analysis to move yourself around in the efficiency versus purity, the phase space. And other than that, it's a vector of where the electron was pointing when it was created. And then you combine them. So it's very, very high level physics, meaningful data to a physicist that ends up in a nano. Am I making sense?
Got it.
So it's fundamentally different as you go from one to the next of these hierarchies.
I see.
But
okay.
It's still, you have every single event. An event exists in nano, in mini, in AOD, and in raw. It's the same event that exists in four different structures,
right.
and possibly multiple versions of the same structure.
Got it. Do you think part of the complexity comes because of this bundling of the object's data? So this one cell that you're talking about. So I mean, the main reason column stores were very helpful was it pushes down the subselection of the data, the projection, to the lowest level possible. And so here is part of the complexity arising because they are getting a lot of the data across the network, and then they're just throwing away most of it.
I think it's, let me answer it, maybe not quite what you asked. I think part of the speed loss from that you see when you go from official data to the custom data formats that my group produces lies in the fact that the official data needs to be type safe, secure. It needs to be guaranteed to have a well-defined meaning, and it therefore ends up having a different representation on disk than in memory. And as you create, there's an exorbitant amount of CPU time just wasted in unzipping and creating memory structures that then are used by the application.
I see.
And so I think part of why when you go to custom formats or to columnar data stores for us, you get these enormous speedups is simply that you give up on all of this.
Got it.
You don't have the same kind you've literally optimized this away, basically gotten rid of it. And maybe I admit freely that this is sort of at the very edge of what I know. There should really be somebody else would be more qualified to answer your question exactly the way you asked it.
Okay. That was insightful still. Thank you. More questions from the audience? We had good participation. It looks like there was a lot of interest. We had more than 35 people today. We have a question on the chat. So Andrew asks, can you share the slides?
Yes, I will. I'll share the slides. Andrew, I'll send you I put the slides somewhere where they are easy to download. It's almost the same slides as I gave to ESNet, full disclosure to Arun as well. But I've added all of the new, the stuff at the very end is all new. So I'll put the slides on some, how about I'll figure something out where I put them so that everybody can access them. Maybe just in my Google Drive.
That would be great, Frank. And if you can send me the link, I can post it on the DB
Yeah.
page.
Yep, I will put it into my Google Drive, and then make it a world shareable.
Thank you. Another question from Mo, can you please provide data samples or link to these formats? All right.
Yes, I could. Send me an email at fkw@ucsd.edu. I don't know, was this in here anywhere? Probably not. Or have Arun connect you, because we have actually I didn't have my email here anyways. That's true.
Oh, that's fine. I mean, if they Google your name, it shows up.
Okay, fine. So there is, CMS has public data sets, and I just have to verify that the public data sets are in the right format. We actually, Javier Duarte, a junior faculty in the physics department, and myself are teaching a capstone project in HDSI this year for the first time, and we're using the public data. And so I'll have to make sure that what exactly that is before I point you to the data that the students on the HDSI capstone are using.
Okay, sounds good. So just to recap, your email is fkw@ucsd.edu. Great. More questions from the audience?
Hi, Frank. Thank you for your for this interesting talk. I have a couple of questions. The first one is, so I know traditionally this worldwide LHC computational grid, they all consist of those beefy clusters located in the universities and the institutes. I'm wondering, are these commercial cloud platforms like AWS or G-Cloud ever used at all in this educational grid?
We have done a variety of different, we use them whenever we get them for free, is the short answer.
Okay.
We can't afford them is the long answer, slightly longer answer. We are perfectly, we've done a years ago, I want to say at Supercomputing 2016 maybe. I'm not sure, I might be off by a year or two, either direction. Where we did this was one of the first years that Google attended supercomputing. And we did a somewhat splashy Google Cloud show off where we ran at 160,000 cores inside Google Cloud, and therefore doubled the capacity of our global processing system. Just by and Google paid for it, but they wanted it during the day, and so if you look at the trace of our utilization, we turned it on in the morning while Google had its stand open. It was running. We turned it off at night, and then it was off overnight, and we turned it on again because even Google didn't feel like they wanted to run during the night at 160,000 cores for us for free. And so we've done this sort of thing, and we're prepared to do it. The software runs, we know how, but it's just not cost effective. It's too expensive.
Okay, so it's mainly the issue of cost, because I imagine these cloud data centers, they face more or less some of the problems you are facing, like the caching and distribution of the data. I guess they are also facing the same problems, and perhaps even already have some solutions already for you.
Yeah, I haven't seen anything that would solve this for me out of the box. Okay. But maybe I've not looked hard enough. The things that I have found, we've done a number of cloud experiments in my group in the last year, and the striking thing that I found was that what the data centers on all three cloud providers are way ahead of on-prem at this point It's way easier to move large volumes of data around in the cloud as long as you're staying within the same cloud. So moving and data around in Google at a terabit per second is easy. Doing anything like this anywhere outside of the big three is impossible, literally impossible. And so they have much better networks. They have much better vertical scalability than we see outside. So we're just starting a project where we're trying to benchmark some of the artifacts that I talked about here for new transfer protocols at the 500 gigabit per second level. And I'm just going to do it inside the cloud because it's easier to do. Because why would I sweat on-prem?
Okay, thank you. My second question is, could you please turn to page 14 of the presentation? Okay, so here I'm not exactly clear what are these. You mentioned there are two kinds of problems you are mentioning. So as far as I know, in these HEP experiments, two things that you normally do. One is that particle flow algorithm that can reconstruct the events, and the other is Monte Carlo. Which one are you talking about here?
Both of them fall into the first category.
Okay.
Think of the distinction being, in the first category, you're turning raw data into AOD, AOD into mini, and mini into nano. You're therefore having to access every single object in every single event in order to calculate whatever output format you want to have. And the step from raw to AOD is very, very costly because you're literally turning, you're turning hits into tracks. You fit helices. And there's a whole lot of pattern. All the pattern recognition happens at the step from raw to AOD, and that's why this is so costly for processing. Down underneath, you don't. It's much more of a select in SQL speak. You're trying to select out of all the events that are there, only the events that you care about, and for the events you care about, you want to calculate a few extra quantities that don't exist inside the data format.
Okay, so the first type of category is how you end up with those AODs. And the second category is, I guess, is it for the end users when they already acquired AODs and
correct. And so the underneath this here is all end user. This here is all central processing.
Oh, I see. Thank you. And my last question is, can you turn to page 34?
Okay.
So you mentioned something about the partial reads. I'm just wondering, for those rows that are marked red, is it possible? Is there any indexing structure that you can sort these rows to enable faster?
Yeah, and people in my field have talked about this, thought about this, tried this, and the fundamental problem why none of this ever worked is very much in the character of the science itself. The character of the science itself is that when we take the data, we don't necessarily know yet all the things that we will want to do with the data later.
Okay.
So we don't, there is no complete schema ever. And therefore trying to index events according to some schema where you would say, this is an event of type A, B, there's another A, and there's an X, and there's a Y, and so forth, is fundamentally not possible because we don't even know what A, B, C, D, E, F, G even is when we create the data in first place. Am I making sense? So
these events, they still consist the raw data. I mean,
no. What I mean is that say a given analysis that gets published as a paper,
Mm-hmm.
often, in fact, many times, the idea to a paper comes out of discussions between theorists and experimentalists, or out of a theory paper as a suggestion.
Mm-hmm.
And then we scratch our heads and say, how would we do this? What kind of selection would I have to make in order to have a fighting chance that I could select the kind of events that this theory paper writes about out of the haystack that I have?
Okay, I get it. So basically what you're trying to select is also part of the research.
Correct. It is not a priori known what even the possible things are that you will be doing with the data that you're taking.
Mm-hmm.
There's always some things are clearly known, but the vast majority, I'd be willing to argue that the vast majority of papers, of the 1,000 papers that we've published so far, many of them are repeats of previous measurements with more data. Fair enough. But all the ones that are not repeats of previous measurements and with more data, all of those are basically, we didn't know that we would be measuring this when we took the data.
Okay. All right. Thank you. That's all my question.
Great. Thank you, Hao. And I must say that we are a little bit over time, but maybe we can take one last question. By the way, Frank, Juha is a PhD student in the database group, and he has a theoretical physics background.
Oh, cool.
Okay. Last question from Umesh on the chat. How much of the data processing is expected to be in real time, at least at the end user level? Trying to understand what service X may look like.
I think nothing is really real time. In realistically speaking, let me actually be a little bit careful answering this question. If I go back to here, none of the above the line is in real time, because to give you the canonical cadence is, we have a commitment that data that is taken with the detector goes through prompt reconstruction today within 4 days of the data being taken. And we give ourselves 4 days because we do real-time calibrations within a day or two of when the data is taken. Those calibrations then we give ourselves a little bit of extra delays to make sure that the calibrations are validated, and then we start prompt reconstruction. So that's the closest to a real-time thing that we have. What is on below the line, you have an aspiration of being interactive. But I make a distinction between interactive and real time. Real time is driven by an external entity and a schedule that you want to achieve. Interactive is when Jane Doe walks in her office and wants to start doing her work. Am I making sense? And so some of that, what you see here, is deliberately phrased, where was it? When I said that the appropriate times is lunch, night, weekend, it's literally because I, as a physicist, I'm a human being. I work according to a human calendar. And I would like the computers that support me to work, to do stuff when I'm not doing stuff, because that adds to my productivity. And so therefore, anything that I can, when I'm working in this part of the chain, I would like to work interactively if I can. When I'm then adding this in, I acknowledge this is too much. I can't possibly, nobody can afford to make this interactive. It's too much data, too much processing. So I'm willing to take this. Short is a lunch break, night, really big ones are weekend. And that's sort of what gives this. Am I making sense? Does it answer the question?
Yep, that sounds good to me. So Umesh, did you have a follow-up question? No,
no, this definitely gives some insight into what I wanted to ask. Yeah. In fact, like part of the question was to know what real times mean in this domain. Yeah, but this answers me. Yeah. Okay.
Thank you.
Now,
Okay.
to be just for fun, because you asked,
Okay.
there is a real serious real time, but it's way. Let me give me 1 sec. Where do I have? I had this here, the trigger and zero suppression. That is real time. That's serious real time. Because turning the 10 petabyte per second into gigabyte per second, that is FPGAs, ASICs, you name it. It's electrical engineering writ large. And I didn't talk about that at all.
Fascinating. That's streaming processing. Okay.
Yeah, this is literally stream processing. We to give you a sense, the first level decision is synchronous at 25 nanoseconds, just buffered back in order to gain some time. And I believe we give ourselves 4 microseconds of buffer space in order to gain time. And then there is that brings down the the 25 nanoseconds to 100 kilohertz. And then there is a big honking cluster that has semi-real-time components, which has GPUs in them in the next round and does full analysis of the data and whittles this down further. So this goes anywhere from ASICs to FPGAs to pseudo real-time.
Fascinating. Okay, great. So that brings us to a wrap of the seminar. Thank you again, Frank. And let's see if we can all give you a round of applause with the icon over here.
Thank you.